This lecture is the second part of a tag team effort. You had 2 lectures in the first week of this winter school by Ivan Deutsch from the University of New Mexico, also on quantum control and measurement. And what I will do is I will cover some of the same ground, but there will be fewer equations and more examples. So that's the idea there. Okay. So what I am planning to do in my lecture today, the first of these 2 lectures, is I want to start out by giving you a brief introduction to the idea that control is a science in its own right. And this will mostly be a talk about control of classical systems and what happens when you transition into the quantum regime. Then I'll talk about 2-level systems, qubits, which are both important in these days, and also the simplest platform on which we can talk about some of the concepts of quantum control. And then at the end, I'll talk about a particular application of qubit control, namely resonance imaging and addressing in an optical lattice. We'll see how much of this we get through. This, in any case, is where I take off my hat as a lecturer and put on my hat as a research presenter. So the level here is going to be a little more advanced. But I should also say that hopefully I'll get through at least some of it, because then you will be able to talk to the graduate students who did this experiment during the high visits. So, pretty much every device that you use in your modern life, any kind of technological device, you can think of as a physical system of some kind, say this, that you guide through some desired evolution. That is, it begins at a certain state, it goes dynamically through some evolution, and it ends at some specific state. If it's something like an airplane, it starts at one gate at one airport, and ends up at another gate at another airport, and you want to be able to go from one state to the other in a way that's safe and reliable and accurate. And how to do this for complex systems is at the core of control science, or what's usually called control theory, which is a discipline that spans engineering and mathematics. The idea that control is a science is as old as the Industrial Revolution. As a matter of fact, the steam engine never really became useful until people developed something known as an engine governor that prevented it from spinning up and out of control. It was a very simple device. You attach a pair of weights to the axle of the steam engine, and these weights swing out as it rotates, and if they swing out too far, they choke off the steam supply. Very simple idea. But already very soon after that, James Maxwell analyzed the phenomenon of hunting that showed up in these systems. That's the idea that if you have a time lag in the response of this device here, then you can get oscillation, right? It chokes itself off too much, then it slows down too much, then it speeds up again, it speeds up too high before it chokes off. And that's really the birth of modern control science. So what's the standard paradigm for control? People usually think of control as involving some or all of these elements. We have our physical system here. There is some kind of controller which takes an input, which are perhaps the desired values for a set of system parameters, or it may be the entire system state. And that feeds some appropriate drive into the system to make the system, make the output of this process, the parameter values of the state, correspond to the input. Often there's a sensor that looks at this output here and feeds corrected information back to the controller so that it can steer appropriately in the presence of errors so that this output is equal to the input, the desired input here. There's of course noise that creeps into this process. Very often one thinks that this is a linear problem. There's a matrix that relates the output to the input. So this, as you know, this is closed loop, right? And most classical control is closed loop because that ensures stability and corrects for errors. Now here is an example of that control problem. There is a starting point down here at the bottom, and there's an endpoint up here at the top. And there's a physical system that's supposed to follow some, hopefully, optimal trajectory between the beginning and the end. And at the end, the system has a controller inside it, and there's even a sensor here that tells the controller whether there's a deviation from the optimal trajectory. This is actually a video So let's try and run it and see how successful this is. Why it's choppy. Let's go back. Oops. Now, just in case you wonder, I didn't shoot this video back in the days where Pierre was still riding a Jeep. Okay? This was just something I found on the internet. I did find out that the person inside was not hurt. I guess that's the benefit of having roll cages when you do crazy things like that. But anyway, this little demonstration here shows some of the things that you have to be aware of when you design a control system. First of all, you have to ask yourself, is the system actually controllable? Meaning, can any possible system state, including the one you want to reach, can they be reached? And in this case here, it's hard to say whether it was actually possible to reach the endpoint. You can also ask, is the system observable? Meaning, can the system state, whatever it is, be deduced by the sensor from the output? And again, in what we just saw, that was questionable. It seemed like the feedback from the sensor to the controller was not adequate to keep us on the optimal trajectory. You have to ask about stability of the whole thing. Are the disturbances damped or at least bounded? I think in the example we saw, we could say that yes, the disturbances were at least bounded. The G ended up at the bottom and didn't go any further. And then finally, we can talk about whether the whole control setup is robust. That is, are uncertain system parameters tolerable, or will they lead to disaster? And if we have problems with any of these, we should do something. If the system is not controllable, maybe we need more actuators, we need more handles with which we can steer it. If it's not observable, maybe we need to add or improve our sensors. If it's not stable and robust, maybe we need to redesign our controller so that it follows another, what we call control law, that is a rule about what to do when certain things happen. So there are two main control strategies, right? There's closed loop control, as we talked about, usually real-time feedback. Sometimes it can be very advanced. The controller might actually try to learn in real time about the system parameters that are relevant. And the most advanced example of that is probably the problem of missile guidance. You want to steer a missile so that it hits an aircraft, but the aircraft is not necessarily just flying in a straight line at a constant speed. It can maneuver in unpredictable ways. So you need a very advanced controller to have it be able to make good guesses about where the target will be based on its past history and what it's doing right now. Open loop is also very often used. The idea in open loop control is usually that you have some cost function, say the distance between the actual state and the desired state that you want to minimize. And just as real-time feedback can be made robust against errors and disturbances, the same is actually possible for robust controls. The idea of open loop control is also fairly old. One of the first things that people thought about really carefully was the so-called aircraft time-to-climb problem, which is as old as military aviation. For example, during the Battle of Britain, it was very important to figure out how you got an airplane on the ground up to a useful altitude at a useful speed as quickly as possible, because you didn't have much warning after you started seeing enemy aircraft on the radar. And because aircrafts are complex, and the lift and the thrust and so on vary in complicated ways with elevation and the thickness of the air, these trajectories here are not at all obvious. You can see, for example, this trajectory involves some going up and then actually diving down to speed up again, rather than just powering really straight up. Okay, now we want to make the system quantum. And in principle, we can think of exactly the same kind of paradigm with a system and a controller and a sensor or a meter, whatever you want to call it. The major fundamental difference is that, well, now we're doing a quantum measurement, right? So in addition to these classical noise sources that can create our technical noise sources, we can also have quantum noise creep in the measurement, and we will, as a matter of fact. And we also know that in quantum mechanics there is a trade-off between how much information we gain about the system and how much we perturb it. Think of this as a cruise control for your nano car, right? If you measure position, you screw up velocity. If you measure velocity, you screw up position. So your cruise control might cause your car to run off the road, in the nano road, in unpredictable ways, perhaps. There is actually quite a vigorous subfield of quantum control that deals with real-time quantum feedback. But I will not talk about that today. I'm going to concentrate on open-loop control, where the toolboxes for quantum and classical control are conceptually pretty similar, except, of course, the details may differ. But in any case, that's the focus of these lectures. Okay, so much for general background in the concept that control is a science. It's a good time if any of you feel like asking any questions. Please interrupt as we go along here. Okay, let's turn to our question. Thank you.
So, in the nice videos Professor Deutsch showed last in his talks, we had an ensemble of atoms, and I'm guessing the measurement component was relatively weak on each atom. So in that case, how much difference do we have from the classical control paradigm?
So I think you kind of answered your own question. In those measurements that he described, you'll be able to see the experiment during the lab visit if you would like. The measurement was indeed weak. Okay, so we had a huge ensemble, about 1 million atoms, and we gathered very little information about each atom. But because we had 1 million identical atoms, when you average that information over all of those atoms, you sort of averaged away the noise and was left with information about sort of the average state of all the atoms. Right? So that's the situation in which we have very little quantum feedback on the individual atoms. Yet you learn something by virtue of having many identical copies. So in that situation, we had sort of worked around the information gain disturbance trade-off that way. So that does not set us up for doing real-time quantum feedback, that kind of experiment.
So here you're talking not about feedback, but about open loop, or at least that's what you're going to talk about right now.
That's correct. What I will now do is I will introduce some ideas about open loop control, and in particular robust open loop control, talking about qubits.
So is there a fundamental difference between open loop control on a quantum system and on a classical system, assuming the classical system can be reasonably complex, which they often are?
Is there a fundamental difference? Well, I would say that the rules that govern the dynamics are, of course, different, right? In one case you have classical equations of motion, and in the other case you have quantum equations of motion. But they can really often be cast in the same way, right? There are some parameters that you want to steer, whether they're probability amplitudes in the quantum system or something in the classical system, and you have some differential equations, usually first-order differential equations, and some matrix that governs the evolution in the two cases. So I would say, I mean, it's a matter of semantics. Do you think using a Schrödinger equation is fundamentally different? If so, yes. But I think the formalism is...
Well, I guess another way of asking the question might be, is there something that tells you that if you're doing open loop, you're not doing closed loop, if you're doing open loop, that you couldn't build a classical model of the quantum mechanical problem that you're addressing?
Yes, I think that... I think that is true. I mean, if you take the example of an angular momentum, just to take a relatively simple one, right? If it is large enough, then we certainly know that there are states accessible to the system that are non-classical. That is, once you start doing something with it, which means doing measurements on them.
Well, that's part of what was behind the question. If you don't do measurements, if you only do control, if you only do open loop control.
Yeah. Well, that's a funny thing, right? What's the point of doing something with the system if you're never going to look at it? You know, at that point in time, I would say it's reduced to a mathematical exercise. You know, you just evolve some probability amplitudes for some parameters. Of course, you have interference in the quantum problem and all that sort of stuff.
Yeah.
But I would say if you don't look at it, the mathematical exercises I think are very similar.
Yeah. Well, maybe it's not worth worrying too much about it, but I was wondering, for example, is there a fundamentally different scaling, for example, an exponential scaling with a complex quantum system that is not, that's only going to be algebraic in a classical system?
To be honest, I don't know.
Yeah.
That's a question I can't answer. Anyone else?
I have a question.
All right.
What do you consider as your environment in the control system?
What do I consider as my environment? So, of course, what you would like to do is you would like to have a dynamical model that describes the evolution of your quantum system, right? And in the most ideal case, you wouldn't even have to worry about an environment. What we're going to talk about today will pretty much ignore the existence of an environment and true decoherence from coupling and entanglement with that environment. But you can certainly put that into your dynamic modeling. Right? And then if you start with a pure quantum state and you desire to steer that to another pure quantum state, you could be in trouble. Because as the system evolves along, you would lose some of that state purity and would not necessarily be able to recover it. So by and large, I think coupling to an environment makes things harder. Because typically when you do quantum control, you're really interested in pure quantum states. Those are the ones that are most useful for things like computation and communication and so on. Okay, let's move on to our qubits. Controlling qubits is of course critical if we take quantum information science seriously. Maybe we're trying to build a mini quantum processor out of trapping atomic ions in an ion trap or sticking them in an optical lattice. And what we typically do is we have some atom, and maybe we're encoding a qubit by picking two levels in a ground state manifold. This is the kind of picture that we will see over and over again today. And then, in that situation, the control objective is to do arbitrary transformations of individual qubits with high fidelity, and hopefully with a high degree of robustness against errors. And actually what you will see is today I'm not going to talk about what people usually call error correction in quantum information science. I'm not talking about correcting for decoherence through coupling to the environment. I'm only going to talk about errors that occur because we're not driving these qubits the way we thought. Maybe because our classical background fields or something like that messing us up. Of course, there's also the question of how you control the many-body system, but that's not a question of controlling qubits. That's a question of controlling n qubits, and that's beyond what we'll talk about today. So I know that two-level systems have already been discussed pretty extensively here. As a matter of fact, the first day of the workshop, and Poul gave us a very nice lecture on the physics of two-level systems and how they can be described in the block picture. But I'll just quickly review that. The first thing that is worth noting is that all two-level systems are isomorphic. They show the same kinds of fundamental behaviors. So they can be mapped onto a spin 1/2 particle. If we have a spin 1/2 particle, pure states are always spin up in some direction. Hopefully most of you are already aware of that. But clearly anyway, we can write an arbitrary state as a coherent superposition of spin up and spin down with some mixing angle theta that tells us how much we have of each, and some phase angle that tells us about the phase in the coherent superposition. And if you write out a state of this type and calculate the expectation value of the spin operator, you find it's h bar over 2 times the unit vector in the theta phi direction in your coordinate system. Okay, so this is spin up in the theta phi direction. If we look at the unitary transformations that are possible on this system, they are geometric rotations, and that's kind of obvious. If all states are spin up in some direction, well, I can go from a spin up state to a spin up state in some other direction by a geometric rotation. We can also look at our quantum mechanics that we usually learn in our first and second semester quantum course, right? The angular momentum is the generator of rotation. And so you have rotations around some axis q. So here's the torque vector, and here is the spin vector that processes around that axis. This would, for example, be a magnetic field. This set, as we heard last week, is a representation of the group SU2, and that's all I will say about group theory. Which is probably a good thing Now, if we're not working with a spin 1/2 system, we're often working with a two-level system with a ground and excited state that are not degenerate. We put on an AC driving field that's near resonance but somewhat detuned. In this case, again, we can define a block vector as the expectation of the Pauli operator, which is the vector whose three components are the Pauli matrices in the basis of these two states. So we can always construct a block vector. And again, analogous to the last page, to the previous page, we can define a state theta phi as the covariance position we had on the previous page. And if the state is pure, that is the density matrix is this, then again the block vector is a unit vector that points in the theta phi direction in some coordinate system, some polar coordinate system, right, that has axes 1, 2, and 3. I like calling them 1, 2, and 3 to remind myself that this system does not live in coordinate space like a real spin 1/2. It lives in some abstract space. So calling these x, y, and z can be confusing. The Hamiltonian, well, in the rotating wave approximation, hopefully we're just reviewing what you remember from your coursework or from last week. But in any case, the Hamiltonian can be expressed in terms of the detuning of this field from resonance and in terms of a resonant Rabi frequency, right, which is a real number in proportion to the amplitude of the field. And one can actually write this Hamiltonian out again in terms of these three Pauli matrices like this. And the beauty of this is then you can see that the Schrödinger equation is just an equation for the spin which processes around some torque vector with some angular velocity, which is the generalized Rabi frequency. Right? So we can always think of the dynamics of a two-level system when the block sphere is having a torque vector and then having the spin or the block vector process around that at this generalized Rabi frequency. The only thing I would point out now is the direction of this torque vector. The three component depends on the detuning from resonance. So if the detuning is 0, you're always going to be in the equator with your torque vector. And then the angle with the y-axis depends on this phase phi of the driving field. And our ability to change the direction of this torque vector, in particular by keeping the detuning 0 and changing the phase, is something that we're going to make a lot of use of. Is this all familiar?
Great.
Yeah.
I think we've seen that, but it's already